will study the derivative of f of z, and from there we will define the Cauchy Riemann, and that is a very special, very useful equation that we are going to study, because these equations, means we use these equations to solve many problems, and they are asked in the entrance exams also. So this part will going to be a little bit of importance, not a little bit, a very important point. And we will also define the analytic function from there. So this is something important in exam point of view. So let us first define the derivative of f of z. So how do we define the derivative? The first condition we put is, let w equals f of z be a single valued function. I talked about this earlier also, that a single valued means that whether we move from one point to another point in any direction. So suppose I have a z plane, and this is x and y axis, and here I have a point Q, and here I have a point P. This Q point is x plus delta x and y plus delta y, and this P point is just x y. So there are so if you want to move from Q to P, there are so many ways from where you can reach P. So the very trivial way is the straight line. Then you could move in a rectangular path like this. So these paths you could take, or else you could even take some very random path and you could reach P. So there are so many ways by which you could reach point P from point Q. But when we say that f of z is a single valued function, it means that it is independent of the path you take. Whether you take the straight line path, or you take this kind of Cartesian, you move in the y direction and then x, or you first move in the x direction and then y, or you just take any random direction like I said. So irrespective of what path you take, you will always end up with the same result, because the end point is always the same. So single valued function means that doesn't matter what path you take, if the starting and the ending points are same all the time, then you should get the same result, a single valued result. So it is path independent. This is what we call a single valued function. Okay, so we here define this f of z to be a single valued function of the variable z equals x plus iy. Then the derivative of f of z is defined as dw by dz is equal to f of z prime. This is how we define the derivative in a symbolic way, and we put limit delta z tend to 0. This is something very similar definition of how we define the limit, the basic definition of the limit. Okay, so this is how we define the limit. that delta z tends to 0, then f of z plus del z minus f of z divided by the difference, this delta z. So we defined f of z to be a single valued with this z variable. Then the derivative of f of z is defined like this, but we can define this derivative under certain conditions, and the condition is that this is valid, or you can define the derivative of f of z provided that the limit we have defined here that exists. So first you have to check that the limit exists, and has the same value. This derivative also has the same value for all the different paths in which delta z approaches to 0. Okay, so the limit exists and has the same value for all the different waves, all the different paths. Or waves in which delta z approaches 0. Okay, so now there is one problem here, and the problem is that you see that q has a coordinate x plus delta x and y plus delta y. If you want delta z to approach 0, that means this deviation or this variation delta x should reach 0 and delta y should reach 0. So once your delta x and delta y is 0, then your delta z will automatically be 0, right? So this is just the variation which you want to make to be 0. It means you will automatically reach delta z to be 0. And when that will happen? When you reach p, because you see p here, p's coordinates are x and y. So you compare this both coordinates, then the variation has reached 0 in x coordinate and in y coordinate also. So basically what you want to do is you want to move from q to p. If you do that, your delta z will become 0. Okay, so we want to make this difference to be 0. Now it is possible, what is the problem here? It is possible that all these paths or many of the other paths could allow you to reach this delta z to be 0, but then it is highly possible that the derivative itself is not existing. So you reached here, but the derivative does not exist. This is possible. Okay, so delta z may tend to 0 in any manner, and delta w by delta z may not exist. This is possible. So then we should have some necessary and sufficient condition to be determined, which will allow us to make sure that the derivative also exists. Okay, so in general scenario, in random way, if you choose any path and you say that you are going to move from this path, in that case delta z may tend to 0, and delta w by delta z may not exist. It is possible that this may not exist. So to resolve this problem, we define or we determine the necessary and sufficient condition okay for dw by del dz to exist, and this condition is okay is the conditions are as follows. So what conditions we should use to make sure that delta z also approaches 0, but in the same path we have the derivative which is existing. So how do we make sure that? So there are two conditions which we need to follow, and the conditions are first condition is let me write first for w equals u xy plus iv xy equals f of z. So for this, the first condition is del u by del x, del u by del y, del v by del x, and del v by del y are continuous. Functions of x and y in the region R in which this function is defined. And the second condition is, and this is going to be very important condition, that del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. Okay, and these conditions or these relations are known as Cauchy-Riemann equations. Okay, or in short they are called CR equations. Okay, so these conditions are to be followed, and from that we make sure that whatever function we have defined, it does have the derivative which is existing. Okay, now once we know this, now we are in a place to define one more very important definition, and that is analytic function. Okay, so a function f of z which is single valued. Again, this function is single valued. I hope now you remember what is single valued. It has the same value following any random path. Okay, so it is path independent basically. So a function f of z which is single valued and possesses a unique derivative with respect to z, so its derivative is also unique, right? So the derivative itself is unique. That means that is also single valued. You can't have multiple answers to the derivative of f of z. So it is always single valued, it is always unique. So your function is such that it is itself a single valued, and the derivative of that function is also unique. Then, and with respect to z, of course we take a derivative with respect to z at all points of a region R. Then such function is called an analytic function. Okay, so to be the analytic function, what are the two important conditions? The function itself should be single valued, and the derivative is unique. Derivative with respect to z is unique. Okay, so function itself single valued and the derivative with respect to z is unique, then such function is called analytic function. Okay, and this is also one more definition might come across in MCQs or somewhere. So function which is analytic everywhere in the complex plane. So you have a complex plane and you got a function which is analytic in the whole complex plane, then such function is called entire function. Okay, so function which is analytic everywhere in the complex plane is known as an entire function. Okay, so that's how we define the entire function. And if u and v are real single valued functions of x and y, such that u and v are real single valued functions of x and y, such that del u by del x, del u by del y, del v by del x and del v by del y are continuous just like this. They are continuous in region R. Then the CR equations, what are they? The CR equations are del u by del x equals del v by del y and del u by del y equals minus del v by del x. These conditions are both necessary and sufficient for a function f of z equals u plus iv to be analytic. So any function which is to be analytic, it has to follow this condition. So these CR equations are necessary and sufficient conditions for any function to be analytic. So what is analytic function? A function which is, so you define a function in a plane and that function is single valued and it has a unique derivative. Okay, so just like this, that doesn't matter what path you take, but it is itself a single valued, and then you define the derivative and that derivative also turns out to be unique. It doesn't have a, so in every path you take a derivative and you end up with different results. That is not allowed. Doesn't matter what path you take, the function will give you a same answer. That means it is single value, and the derivative of that function is also unique, is also single valued. Then such function is called analytic function. Okay, so that these are very important notes to be known, because this will be used now in the next part when we will solve the problems. And there are at least one question in entrance exams in which you have to find out, or you have to determine that whether the given function is the analytic or not. And how will you know that the function is analytic or not? You will check the function by plugging in this CR relations, and if the relations are valid, means if the function follows this relation, then you say that the function itself is analytic. So this is something very important that you will come across at least one question in entrance exam. So next time we are going to solve the problems on analytic function, that how to check whether the function is analytic or not.